Welcome to the course module of communication engineering. So far we have discussed about the amplitude modulations and angle modulations in my previous lectures. So now today I'm going to start one more topic, which is our digital communication. So let's begin this particular topic. In digital communication, first of all, I would like to make you aware that in case of analog communication, if you see that we have studied like AM modulation and frequency modulation, or you can say angle modulation. In that case, what we have taken is we have taken the analog uh, massive signal. Okay, so we were talking about the voice signal, audio signal, and video signals. Okay, so we were talking about the analog signals, and that analog signals is actually used for modulating the continuous wave. Okay, so it was a very high frequency analog carrier. Okay, so basically analog signal was actually modulating a continuous wave. Okay, continuous wave. Okay, that was our sinusoidal wave, so of high frequency that we have already seen. In case of digital communication, the basically the massive signal that we have to use is generally not analog in nature. Okay, it is generally that we take is a digital massive signal that we have to take. So basically what we do is, first of all, once we have an analog massive signal, then first we need to convert the analog massive signals into a digital form, in a suitable digital form. Okay, and then based on the requirement of whether we have to go for the baseband data transmission, or we have to go for the band pass data transmission, we have to appropriately do a modulation scheme. Okay, we have to appropriately choose a particular modulation scheme. So here you can see that in the case of baseband data transmission and the band pass data transmission, if you see, first you must have understand that the massive signal should be a digital massive signal. Okay, so all the analog massive signal has to be converted into digital form, and then that digital massive signal will be modulating a particular pulse. Okay, it will be used for modulating a particular pulse. So you remember that that analog massive signal can be used for that digital massive signal can be used for modulating either pulse, or it can also be used for modulating a continuous wave. So here we can see that in the case of band pass data transmission, after having a like digital massive signal, that massive signal has to be multiplied with the high frequency continuous wave. Okay, high frequency sinusoidal carrier. Okay, so in this case, band pass data transmission, this digital massive signal has to be multiplied with the high frequency sinusoidal carrier. But in the case of baseband data transmission, there is no such requirement. You remember that here we just have the pulse. Okay, and that pulse has to be modulated in a certain way. Okay, for example, the baseband data transmission is further divided into pulse analog modulation, and another portion is called pulse digital modulation. Okay, so we will discuss it one by one, like what is pulse analog modulation, what is this PAM, PWM, and PPM. For example, PAM stands for pulse amplitude modulation, PWM stands for the pulse width modulation, this is pulse position modulation. Similarly, in the case of pulse digital communication, we are having pulse code modulation, then this is DPCM, okay, differential pulse code modulation, then delta modulation, then adaptive delta modulations. So these are the different modulation schemes which is falling under the baseband data transmission. You remember that why we are calling it as a baseband data transmission, because while transmitting the signal, only baseband channel is used. Okay, for example, we can use the mostly the wired media that we are using. Okay, that will be a baseband transmission media. Okay, so we are using a baseband data transmission technique, and that's why we are calling it as a baseband transmission. Okay, baseband data transmission. In the case of band pass data transmission, obviously its name suggests it is a band pass data transmission. We have to use a transmitter, and that transmitter will be converting the VI waves into the electromagnetic waves, and that electromagnetic waves will travel through a particular wireless media. So here we are using the wired media for transmission, okay, and here we are using the wireless media for transmission of the same digital message signal. Okay, so that we have to look at. So you try to understand the difference between the analog communication and the digital communication. Here we are using the pulses. Okay, first of all, message should be in a digital form, and then that message should be used for modulating either pulses. Okay, either pulses, or it can also be used for modulating the high frequency sinusoidal carrier. As compared to analog communication, in the analog communication, both the message signal as well as the carrier are both the continuous time signals. Okay, it is an analog. In analog communication, message signal will also be an analog message signal. Okay? It is not a digital message signal. So let's see how these things can be done. Okay, here you can see in the band pass data transmission, it is further divided into binary signaling and M-array signaling. So, okay, in which we are having certain modulation scheme like ASK, FSK, PSK, which is known as amplitude shift keying, frequency shift keying, and phase shift keying. Similarly, we are having M-array signaling techniques, which is called as QPSK, 8PSK, and 16PSK. So I will be discussing all these topics. Okay, whatever falls under our syllabus. Okay, I will be discussing all those topics. So first, you try to understand that what is digital signal. Okay, so you try to recall my second lecture. Okay, either it is a second lecture or a third lecture, you please go through it. I have discussed about what is analog signal and what is digital signal. So just for your convenience, I am repeating the same thing again. Okay, so here you can see that basically any signal, if we have any signal, to qualify it as a digital signal, the only requirement is that its amplitude should be discretized. You remember that any signal, any arbitrary signal, if it is having a discretized amplitude, then it can be qualified as a digital signal. You remember digital signal can be a continuous time. Okay, here in this case, we can see that for each and every instant of time, this signal GT is being defined. Okay, but you can see that this GT is just taking two different levels. Okay, so it is having just two levels. Okay, it is having a finite set of values that it can assume. So basically, it is just having two levels in this case, and therefore we are saying that it is a digital signal. You remember any signal, okay, any signal which is taking only finite set of amplitudes. It is not necessary that it is two only. It can be three, it can be four, it can be five, or anything. If it is anything finite, okay, that can be classified as a digital signal. Okay, similarly, here it is a discrete time digital signal, in which you can see that the amplitude of this GT is constant. Okay, here means it is taking a finite set. Okay, like here it is taking a certain value, and again it is taking another value. It is just taking two different levels. And now we can see that this digital signal is also discretized in time. It is not only the amplitude portion which is getting discretized, but its time portion is also getting discretized, and therefore it is also classified as a discrete time digital signal. So you remember that for a digital signal, time is not a factor. Okay, discretization of time is not necessary, because in both the cases you can see that here it is a discrete time, here it is a continuous time, but both the signals are regarded as a digital signal. The meaning is that the only amplitude discretization is necessary for a signal to be qualified as a digital signal. So now if you understood this, I just wanted to make you aware that whenever we talk about digital communication, you may be confused here that if it is a continuous time digital signal, then maybe the time discretization is not required. But what you will find that in most of the cases, when we convert an analog message signal into a digital signal, we need to perform both time discretization as well as the amplitude discretization. And later on, the signal can be converted into a continuous time digital signal wherever it is required. Okay, wherever it is necessary to have this type of digital signal, then later on it can be converted. But first of all, while converting a digital signal into an analog signal into a digital signal, we need to discretize both time and amplitude of the arbitrary signal. So let's see how this can be performed, that we have to look at in this particular discussion. Okay, how it can be done. So to perform that, we can see how to convert an analog signal into a digital signal. So let's suppose Basically, there are two basic steps you can find. The first one is the sampling, which is called as the time discretization. Okay, sampling, which is called as time discretization, and the second one is called as the quantization. Okay, the quantization means it is an amplitude discretization. I hope you must be able to understand from this. Okay, so sampling means we are doing the time discretization of the signal, and then quantization means amplitude discretization of the signal. So let's say if we have any arbitrary analog signal xt, okay, not necessary that it is periodic or non-periodic signal. Let's say if it is an arbitrary signal xt, okay, then we have to talk about what is the maximum bandwidth or the maximum frequency component that this arbitrary signal xt is having. So let us suppose if for this particular analog signal xt, then first of all, what is the sampling? Sampling is referred to as a time discretization. So how to do this time discretization? So basically we have to take the value of this xt, whatever it is assuming over a time, continuous time, we have to discretize, discretize the time axis. Okay, so what we can do is we will be taking the samples of this particular xt, okay, samples of this particular xt at a regular interval of time. So suppose that regular interval of time at which we want to take the samples, for example, this regular interval can be of like depending on what is the maximum frequency component of the xt. Let us suppose if ts will be measured in obviously in the seconds, so it can be in the like 10 microseconds or 100 microseconds, okay, or it can be in the milliseconds also, depending on what is the maximum frequency component of the xt. So this time interval in which we are taking the samples of the xt will be a constant. Okay, so for example, in this case what we are doing is we are not talking about the all values of the xt, okay, of all values of the xt are at every instant of time, but rather we are talking about the some regular interval of time. We have to talk about what is the value of the xt. For example, at this portion we can take the sample of the xt, okay, we can at this time instant, okay, and after ts second, capital ts second, we will again take the sample of this particular xt. So rather having this continuous time signal, what we can have is we can have a discrete time signal like this. Okay, this will be our discrete time signal. So that discrete time signal will have just these values. Okay, these values at every regular interval of ts. Okay, so that sampled value we will be having. Fine. So this is what we are doing as a sampling. So we are doing this sampling. Okay, so sampling means we are discretizing the time axis. Now there is a Nyquist theorem. Okay, so first of all, we have understood what is sampling process. The sampling process is discretizing the time axis, and at a regular interval of time space, okay, we have to take the samples of this arbitrary signal xt. Okay, now the question is, what should be the value of ts? Okay, what should be the value of ts? Is there any particular limit in which, or a particular rule that we need to follow, so that from this sampled value, okay, from this sampled value of the xt, is it possible to recover back, or we can reconstruct the original message signal or not? This is the question. Okay, so what is I want to explain here is basically there is no we cannot take any value of the ts. Okay, we cannot take any value of the ts. There is a certain criteria that we need to follow while doing the sampling of a particular analog signal. So that particular criteria is actually given by the Nyquist. Okay, so we are talking about the Nyquist theorem. So what this Nyquist have said is, let us suppose if we have any arbitrary signal xt, okay, and if its xt, its Fourier spectrum is known to us, and let us say that the Fourier spectrum of the xt is something like this. Okay, something like this shown in this particular picture. Okay, so let us suppose we have any arbitrary analog signal xt which is band limited to a frequency of fm. Okay, please, here it is written as band limited to w, and I have also written the expression for w, so you just make it w. Okay, in the figure, just you assume that it is w. So what I'm saying is, let us suppose we are having any arbitrary analog signal xt whose Fourier spectrum is known to us, and it is having its maximum frequency component is equals to W. Okay, so beyond W there are no frequency component available in this particular xt. So what we can write is this particular statement that if it is band limited to W, it means that the Fourier spectrum xf equals to 0 for mod f greater than W. Means whenever the frequency is greater than W, okay, either it is positive or it is less than minus W, then the spectral component will be 0, because the spectral component is only occupying a bandwidth of 0 to W. So that's why this statement says that, let us say it is band limited to W. Okay. Now, if we do the sampling, okay, of this particular signal xt, if we go for the sampling process, then basically this continuous time variable t will be converted into a discrete time variable. Okay, it has to be discretized. So how it can be discretized? We will be converting t equals to nts. Okay, so this t will be converted into nts. Now this ts is a particular constant value and n is an integer value. Okay, you remember that we are substituting t equals to nts. It means that n is an integer value that we are taking, so it will be taking like values from minus infinity to infinity, and it is an integer value, so it should be minus infinity. If you can write, it is minus 3 minus 2 minus 1 0. Okay, 1 2 3 4 5 so on. Okay, so it will be an integer value, and ts is the sampling interval. Okay, what we can say that ts is nothing but our sampling interval. So let's say that if we are talking about the sampled value of the xt, which is defined equals to x equals to x nts, okay, then from this sample, okay, from this sample that we have defined here, okay, it is xst. Okay, so we are talking about the sampled version. So from the sampled version xst, okay, this massive signal xt can only be recovered back by a certain method when this this time interval ts, okay, that we have taken for sampling, okay, this ts is less than equals to 1 upon 2w. You remember that this is the Nyquist theorem. Okay, what Nyquist says that if this time interval of taking the samples, okay, or sampling time, you can say, if this sampling time is less than equals to 1 upon 2w, or we can also say that what is the sampling frequency fs. So sampling frequency fs will be defined equals to 1 upon ts. So basically the sampling frequency fs, if it is greater than or equals to 2w, where w is the bandwidth of the massive signal, then it is possible to reconstruct the xt, okay, reconstruct the xt from its samples x and ts. Okay, so what we are saying that if sampling frequency fs is greater than or equals to 2w, then only this samples can be used for reconstructing the original massive signal. So the meaning is that if fs, or the sampling frequency fs, is less than 2w, then there is no possibility that the samples that we obtain that can be reconstruct the original massive signal xt. Okay, so you remember that when we are doing the discretization in the time, okay, whenever we are doing this discretization, we are actually losing the information between the two sampling interval. Okay, because here we are taking the sample, and after a t second we are taking the another sample or the next sample. So in between we are not taking any samples. Okay, we are not taking any samples, so we do not know what will be the value in between. Okay, and therefore it is required that to reconstruct, if you want to reconstruct the original massive signal, the sampling frequency should be greater than equals to 2w. Okay, if it is not, then it is not possible to reconstruct back the original massive signal xt from its samples. So this is what our Nyquist theorem says. Okay, now if you understood this, how to perform the sampling, okay, how to perform the sampling, now we have to talk about the type of sampling. Okay, there are three basic types of the sampling that we have. The first one is the ideal impulse train sampling. Okay, then the second one is the rectangular pulse train sampling, and third one is the flat top sampling. So first of all, we have to understand why it is so, why if fs is less than 2w, why we are not able to recover back the original message signal. So first, to understand that one, I will be discussing about the ideal impulse train some sampling. Okay, so how it can be performed, that we have to look at first. So in the case of ideal impulse train sampling, what we have to perform is we have to take the our arbitrary message signal, and then this arbitrary message signal has to be multiplied with the impulse train. Okay, and let us say that here it is in the picture, it is not shown. The impulse train is having its time interval, you can say, or you can say the time period of this particular impulse train is equals to ts. Okay, let us say it is ts. So at every instant of ts second, one impulse will appear. Okay, so how to perform this sampling, that we have to understand. Okay, so basically what we do is we are taking the message signal, arbitrary message signal, and then this arbitrary message signal has to be multiplied with the an impulse train. Okay, a series of impulses, you can say. We are saying that impulse train means it is a series of impulses. Okay, and that impulses is actually generating at the speed of sampling frequency fs. Okay, that fs will be equals to 1 upon ts. Okay, 1 upon ts. So between the consecutive samples, there is a duration of equals to ts. Okay, which is a sampling time. Fine. So at every sampling time ts, one impulse is going to be generated, and then there should be a particular circuitry that should be able to multiply this message signal xt with this particular impulse train. So we are saying that it is an ideal impulse sampling. Okay, you try to understand it is the ideal impulses, because you remember that in the practical cases we cannot generate an ideal impulses. Okay, we cannot generate ideal impulses because if you know about the impulse definition, impulse is having its width equals to 0. Okay, so we cannot generate anything which is having its width equals to 0. Okay, so that width should be equals to 0 ideally. But generally in the practical cases, whenever we generate, we try to generate an impulses that will have a finite bandwidth, finite width. Okay, in the time domain. Okay, it will have a certain finite width. It may be of 1 nanosecond, it may be of 1 picoseconds. There must be certain finite width of the impulses. It cannot be 0. Okay, so this is what I'm telling about the ideal impulses. Okay, so I'm just talking about a theoretical calculation. Okay, at present. So basically what we can do is we can generate an ideal impulses, and that ideal impulse train can be multiplied with the xt. And once it will be multiplied with the xt, whatever be the magnitude of the xt, that magnitude will be taken by this impulse train. Okay, so its impulse train magnitude will be modulated by the amplitude of the message signal xt. So now it is something like this, this sampled version we are going to obtain. Okay, so how it can be represented mathematically, that we have to see. So basically this xt has to be multiplied with the impulse train, ideal impulse train. Okay, so how this impulse train can be represented mathematically, it can be represented by this particular equation. It is n equals to minus infinity to infinity, and it is delta functions. Okay, because it is a impulses, so it has to be represented by a delta function t minus nts. So obviously when equals to n equals to 0, then a impulse train will be appear at t equals to 0. Okay, then it will be at t equals to when n equals to 1, you will substitute, you will be get an impulse train at equals to t equals to minus ts, t equals to ts. Okay, then t equals to 2 ts, then t equals to 3 ts, 4 ts, and so on. Okay, and therefore this particular mathematical expressions represent you a ideal impulse train. Now when you multiply these two equations, okay, xt and this ideal impulse train, you can write the sampled version xst equals to n equals to minus infinity to infinity, and xt delta t minus nts. Okay, now we can use one property of the delta function, that if we are multiplying any function xt with the delta function like t minus ts, at that time this x will be xt, t will be replaced by equals to and minus nts, means t equals to nts. Okay, you try to remember, I have already discussed about this property in my second or third lecture. Okay, so in this case what we can have is, after multiplying this, this xt will be taking the values at t equals to nts. So what we can substitute here is x nts delta t minus nts. Okay, so this will be the sampled version of our massive signal xt. So this represents xst represents this particular waveform. Okay, it is representing this particular waveform. Fine. So basically this delta function is actually modulated, or it is taking the amplitude of our massive signal at a different time interval. Okay, at different time instant. Okay, which is defined as equals to t equals to nts. Fine. So that's why its amplitude is actually multiplied. The amplitude of the delta function is actually multiplied with x nts. Fine. So here we are having the nts. So whenever we are changing the value of n, accordingly we are shifting we have to talk about the xt value at different instant of time ts. Okay, either it is at 0 ts means x0, or it may be ts at 2 ts or 3 ts. Okay, so that value has to be there should be a magnitude of this our impulse stream. Okay, should be a magnitude. So this will be representing our sampled value of our massive signal xt. Now I request all the students, please go through any of the signals and system books and try to work out what will be the Fourier spectrum of this particular impulse train. If we have any impulse train in time domain, what will be the Fourier spectrum of this impulse train? Okay, so that you please try to work out, because I'm directly using the result. Okay, in this our discussion, that discussion here, it is not necessary how to obtain this particular expression. Okay, so try to work out, we can directly use the result. Okay, you will definitely find this solution in the various signals and systems books, or even you can work out and you can get this particular result. Okay, so you will find that for any impulse train, the Fourier spectrum of the impulse train is again going to be an impulse function only. It is again an impulse train only. Okay, and that will be scaled by a factor of 1 upon ts, that you remember. Okay, if it is having a separation between the impulses is equals to ts, then the magnitude of the Fourier spectrum impulse will be scaled by a factor of 1 upon ts. So basically when we take the Fourier transform of the equation number 1, as we know that in the case of multiplication in the time domain, it will be converted into the convolution in the frequency domain. Okay, so if xt is having its Fourier transform equals to xf, and if this delta t minus this impulse train is having its equivalent Fourier transform, then the convolution between the two will give the Fourier transform of this particular sampled signal xs3. Okay, so that will be our Fourier transform. Okay, so now if we have this Fourier transform, if you do the this convolution, okay, you will find that the convolution between xf and any delta function is similar to this. Okay, it should be converted into xf minus n upon ts. Okay, these portions I have already discussed in my previous sections. Okay, you try to recall those discussions in which I have talked about the amplitude modulation. Okay, there I have already discussed this all properties. Okay, so basically when you convolve this particular signal, then whatever be the convolution will be giving you the result of xf minus n upon ts. Okay, so this will be the convolution. Okay, the result of the convolution. So basically the function that we are going to get is the result of this convolution is 1 upon ts n equals to minus infinity to infinity xf minus n upon ts. Similarly, 1 upon ts can be written as the sampling frequency fs. So you can write here xsf equals to 1 upon ts, and here it is xf minus n fs. Okay, now we have to try to see the what will be the spectrum of this particular function. Okay, of sampled version. Okay, so let us assume that in the previous case, the way we have taken the we have assumed the Fourier spectrum, or the spectrum component spectrum of this xt equals to xf. Okay, So whatever be the spectrum, okay, let us suppose that if we take this particular spectrum of the XF, okay, let us say this is our message signal XT and whose Fourier spectrum is something like this, okay, then what this represents, okay, you try to see this, okay, what this represents, okay, so it is the uh, shifted version of the message spectrum, okay, and shifted around f equals to fs, f equals to 2fs, f equals to 3fs, similarly f equals to minus fs, minus 2fs and minus 3fs and so on, okay, up to infinity. So basically if you see this particular expression, this magnitude is scaled by a factor of 1 upon ts, okay, the magnitude is going to be scaled by 1 upon ts, and then when n equals to 0, then the spectrum will be equals to xf, okay. So this portion is remain same at x equals to f equals to 0. So this is first portion, okay, when n equals to 0, so its magnitude becomes 1 upon ts, and this bandwidth is taking from minus w to w. When n equals to 1, okay, when n equals to 1, this spectrum of the message signal is going to be shifted around f equals to fs. So this is our f equals to fs, okay, and this same spectrum has to be shifted around, okay, so it is shifted here. Again the magnitude will remain same, which is equals to 1 upon ts and so on. Again we have to repeat the same spectrums, okay, remember that we have to repeat the spectrums here, okay. Similarly when n equals to minus 1, at that time at f equals to minus fs, there will be again a same spectrum, okay. So basically while doing the ideal sampling, okay, with the impulse train, whatever be the spectrum of the massive signal, that spectrum is going to be shifted around the integer multiple of the sampling frequency fs, okay. So it will be shifted around integer multiple of the frequency fs. So this type of a spectrum and infinite such bands we are going to obtain, okay, we are going to obtain such infinite bands. Now you try to see this conditions, okay. What is the first condition is, as per our Nyquist theorem, what we have said is, if sampling frequency fs is greater than equals to 2w, okay, if it is, so first consider that if it is greater than 2w. So basically when it is fs is greater than 2w, that time you can see that if this is our fs, then this portion will be our fs minus w, because we know that its lower limit is minus w. So here it will be fs minus w, okay, when this value is fs, okay. So this particular portion will be fs minus w. Now what we can do is we can calculate whether there is a gap between these two portion or not, okay. So if you subtract from this higher portion to this lower portion, okay, because this is our first band, okay, then we are going to get another band at this, then the next band again, okay, and similarly and so on, okay, we are going to get both the sides. So if we calculate fs minus w is greater than 0, okay, because this gap is visible to be more than 0, okay, it is not equals to 0, then the fs is greater than 2w, okay. Here we can see that if fs is greater than 2w, obviously this portions of this particular consecutive bands are not overlapping, okay, it is not overlapping. If it is fs equals to strictly equals to 2w, okay, then you remember that whenever it is fs equals to 2w, then this higher portion, okay, of this particular section and this particular section is going to be meeting at this value of w, okay, because you can calculate easily, okay, we can easily calculate this value is equals to fs, so this value will be equals to fs minus w, and because this is 0, this value will be equals to 0 w. So basically this value is nothing but fs minus w, okay, minus w equals to 0, because width is 0, there is no gap, okay, and therefore we can see that whenever the sampling frequency fs is equals to 2w, that time there will be no gap between the two consecutive bands, okay, or you can say the side bands, okay, there will be no consecutive gap or spectral gap between the two consecutive side bands, fine. Similarly, if you take fs less than 2w, if it is fs is less than 2w, then you will be finding that these consecutive spectral components are going to be overlapping, okay, a certain portion is going to be overlapped whenever fs is less than 2w. So you remember that it is very easy to analyze this one. Okay, whenever fs is greater than 2w, this is called as the oversampled signal. Okay, it is oversampled signal. Okay, whenever fs is equals to 2w, it is strictly sampled. Okay, at the Nyquist rate. Okay, because the minimum sampling frequency that we should have is fs equals to 2w. You remember that as per the Nyquist theorem, fs should be greater than or equals to 2w. So what is the minimum sampling frequency that we require is fs equals to 2w. Okay. So whenever fs equals to 2w, there will be no gap between the two spectral component. Okay. And at this time, while recovering back the original masses signal from its sampled version, we need an ideal low pass filter. You remember, because there is no gap between the two sideband frequencies. Okay. Between two adjacent sideband components, spectral components. Okay, so here we are having fs equals to 2w. There is no overlap. Okay, but we need ideal low pass filter to recover back the original passive signal. But when fs is less than 2w, there is a spectral overlap that we can observe in this particular picture, and which is called as the undersampled signal. Okay, so whenever the signal is undersampled, then it is not possible to recover back the original massive signal. You remember that how to recover back the original message signal from the sampled version. So you can see this is our message signal spectrum. Okay, this is our message signal spectrum, and this is the sampled version spectrum. Okay, when fs is greater than 2w. So basically, if you want to just extract the message out of this sampled version, if I pass this particular sampled signal through a ideal low pass filter, okay, ideal low pass filter with bandwidth of w, okay, then only this much of portion can be extracted, and all the higher frequency component can be rejected, and this massive signal can be extracted easily whenever fs is greater than 2w. But in case of fs equals to 2w, the low pass filter that we required is an ideal low pass filter. Here we can have a practical low pass filter. What is the difference between the ideal low pass filter and the practical low pass filter? In the case of ideal low pass filter, there will be a brick wall approximation. Okay, there will be no transition bands. You remember that there will be no transition band. We just have a pass band and directly we have a stop band. Okay, but in case of practical low pass filter, we will be having a certain transition band. Okay, so there will be a certain transition band in which the pass band, in between the pass band and the stop band, there will be a transition band. So some portion of the other components, all these frequency components may also be allowed. Okay, so basically here we can design an ideal low pass filter. Okay, means practical low pass filter because of this gap. Okay, because of this spectral gap, so that this portion cannot be means can be rejected easily. But in this case, we cannot we cannot have a practical low pass filter, because if you take the practical low pass filter, a certain adjacent frequencies will also be selected, and that time the recovered massive signal will not be distortionless. It will contain a certain amount of distortion. Okay, or certain other frequency components will also be present. Okay. And here in this case, when it is fs is less than 2w, which is undersampled case, obviously in this case, ideal low pass filter can also not work. Okay, it cannot be used because there is a spectral overlap at these portions. Okay, a certain portion is getting overlapped at this particular region, and therefore our signal is going to be distorted. So basically, this reconstruction of the massive signal is not possible whenever we are doing or we are performing the undersampling. Okay, and that particular spectral component is going to give a particular distortion, okay, in the reconstructed signal, and that error is actually called as the aliasing. You remember that that error is called as the aliasing. So I hope you must be able to understand how to demodulate a PAM signal or reconstruction of the xt from its sample version. We have to sample it, okay, with the Nyquist frequency or greater than the Nyquist frequency, and then we have to pass it through an low pass filter with appropriate bandwidth, so that we can get back the original massive signal. So I hope you must be able to understand how this ideal sampling is performed. Now, as I said that it is not possible practically to generate an ideal impulse train. Okay, so what we can have is we can have the an impulse or a pulse train of finite width. Okay, of finite width. So let us say if we have, instead of having an ideal impulse, okay, we can have a pulses of finite width. Okay, so let us say we have a pulse of finite width. Let us say it's the width of this pulse is equals to tau, and then this particular pulses is actually generating in every ts second. So sampling time again is a ts, okay, and then the width of this particular pulse is equals to tau. Okay, so if we have this is the most means more practical version. Okay, in the practical cases we can generate this type of pulses only, we cannot generate an ideal impulse train. So when we multiply this rectangular pulse train, if you multiply, suppose that if we multiply, because it is taking a constant value, okay, if you multiply a constant with this particular waveform, so you remember that during the duration of tau, whatever be the variation of the message signal xt, the same variation is going to happen in this particular duration. Okay, so this is not going to be a constant. Okay, obviously its amplitude is going to be decided by the amplitude of the xt, because we are multiply the xt with this ypt. Okay, this rectangular pulse train. So when you multiply it, whatever be the form or the variation in the xt, the same variation will also appear for the duration of tau in this particular multiplied version of the pulse train. So here you can see that it is taking this shape again. Here it is taking this shape. Okay, again here it is taking this shape. Okay, so whatever be the shape of the message signal, the same shape for the duration of tau is going to be appear in the multiplied version of this particular two signals. So now let us suppose if we want to perform the sampling by having this rectangular pulse train, what we can do is we have to multiply these two signals xt multiplied with the this finite pulse trains. Okay, so if we multiply, what we can take is, again you can go for the Fourier transform of these above equations. So this Fourier transform is going to give you x sf equals to xf. Again it is a convolution between this xf and the Fourier transform of this particular pulse train, that will be ypf. Again I request all the students, please go through the signals and system books and try to find out what will be the Fourier transform of a rectangular pulse train. You will find the solution for this Fourier transform of the rectangular pulse train. I am directly using the results here in our discussion. Okay, so for a rectangular pulse train, the Fourier transform is actually given by this particular expression, which is ypf equals to n equals to minus infinity to infinity. It is tau upon ts. You remember what is tau? Tau is the width of the pulse train. And what is this ts? Ts is the sampling interval. Okay, it is a sampling interval. Okay, so tau upon ts, it will be a sinc function. So sinc function n fs tau. What is fs? Fs is equals to 1 upon ts. Okay, which is a sampling frequency. Fine, it is a sampling frequency fs. So sampling frequency means how many samples we are taking per unit time. Okay, you remember that, how many samples we are taking from a particular message signal, okay, per unit time. Okay, so that will be our sampling frequency, which is equals to 1 upon ts. Okay, so n fs tau, and it will be a delta function f minus n fs. Okay, so that will be the expression for the Fourier transform of our rectangular pulse train. Please, I request all the students, please work out this one. Okay, it isn't required, you please work out this one, so that you will be having a confidence that this is the Fourier transform of this particular pulse train. So once we have this pulse train, now what we have to do is, again we have to do the convolution between the xf and this particular Fourier transform ypf. So once you perform this, after doing this convolution, the final result that we are going to get is xsf equals to n equals to minus infinity to infinity. It is tau upon ts. Again a sinc function, okay, sinc function nfs tau, and this delta function when convolved with the xf, again we have to go, we are going to get the shifted version of the message signal. So it is again xf minus nfs. Okay, so this delta function will be replaced with xf minus nfs. Okay, we are using the property of the convolution with the delta function with of any other signal. Okay, so that will be our xf minus nfs. So if you expand this particular summation, which is an infinite series, we can have the infinite number of terms. Okay, I'm just writing these three terms corresponding to n equals to -1, n equals to 0, and n equals to +1. So here you can see that this portion is tau upon ts. It is a sinc function. We are substituting here. It is n equals to -1. You can substitute. Okay, you will find that it is a sinc function is an even function. Okay, you remember that you try to plot the sinc function. Sinc function is an even function. You will get sinc equals to tau upon ts x f plus fs. Okay, we are substituting n equals to -1. Then if you substitute n equals to 0, okay, you will find that the sinc function will take value equals to 1. Whenever n equals to 0, you will find that sinc 0 equals to 1. Okay, so it is tau upon ts xf. Okay, then plus n equals to 1, you substitute n equals to 1, so you will be getting tau upon ts sinc tau upon ts and x f minus fs. So everywhere you are going to get this particular factor tau upon ts. Okay, and then we are going to get this sinc function tau upon ts, then 2 tau upon ts, 3 tau upon ts, 4 tau upon ts, and so on. Okay, and there will be a such infinite series. Now try to plot this particular function. Okay, try to plot this particular spectrum when we are having a rectangular pulse train. Okay, rectangular pulse train. So when we have this rectangular pulse train, now I'm just trying to obtain the spectrum for tau upon ts equals to 1 upon 10. Okay, so if we substitute means the sampling interval is 10 times the width of the pulse. Okay, what does it mean? Tau upon ts equals to 1 upon 10 means this sampling interval ts is 10 times uh, the width of the pulse string. Okay, because you can write ts equals to 10 tau. It means that the sampling interval is 10 times the width of the pulse string. So basically tau equals to ts. If you substitute this value, okay, you can substitute 1 upon 10 here. You can calculate the sinc function value. Okay, tau upon ts is equals to 1 upon 10. You will find that this value is 0.0983. Okay, similarly, you can also calculate alpha 2 value. Okay, means this value when n equals to 2. Okay, so when n equals to 2, you will get 1 upon 10 sinc 2 upon 10. Okay, so that value is equals to 0.0935. So basically what we can see is in this middle portion. Okay, here we are getting a tau upon ts xf. So this portion is actually if we have the massive signal spectrum equals to xf. Okay, the same spectrum is to be there around the f equals to 0, but the magnitude will be scaled by a factor of tau upon ts. So when tau upon ts we have taken is as equals to 1 upon 10, so this value is going to be 1 upon 10, and this will be our spectral component. Okay, this is our spectral component. So when our n equals to like 1, that time this spectral component has to be shifted around f equals to fs. So it is at f equals to fs, the same spectral component is going to be shifted around. Okay, and then we are having this component equals to fs minus w. Okay, this component will be fs plus w, and there will be a certain magnitude. Okay, that magnitude I am denoting it as equals to alpha 1, and that alpha 1 I have calculated over here, which is equals to 0.0983. Similarly, you can go on calculating for n equals to 2. We can have the alpha 2 value. You will find that this alpha 2 value is coming out as 0.0935. So basically you try to compare the spectral component. Okay, spectrum. When we have taken the ideal impulse for multiplication, okay, in that case all the spectral components or sidebands whatever we got, the infinite sidebands have the equal amplitude. Okay, it has the equal amplitude. But in the case of a sampling with rectangular pulse stream, the only changes that going to occur is that the amplitude is going to decrease as we increase the value of n. Okay, when we go for the higher bands, okay, n equals to 2, 3, 4, and so on, you will find that this spectral component is going to reduce. Okay, it is going to reduce. So this is the only difference, okay, between the two spectral component when we talk about the ideal sampling and we talk about the rectangular pulse field sampling. Okay, so again, the recovery of the original massive signal from a sample version is very straightforward because our massive signal lies within this band. Okay, so we can pass this sampled signal through a low pass filter. Okay, a practical low pass filter can be inappropriate, means can be useful, can also be used. Okay, in this case because there is a spectral gap between the adjacent side bands, and therefore what we can have is we can pass it through a filter, low pass filter of appropriate bandwidth, and then the original massive signal can be reconstructed. Okay, we can reconstruct it easily from this sample version. Now I'm just talking about briefly the flat topped sampling. Okay, in the case of flat topped sampling, what happens is basically we have to take the massive signal xt, and that has to be multiplied with the ideal impulses. Okay, and then we have to follow a zero order hold circuit. Okay, zero order hold circuit. So I'm not talking about means I will not talk much about this particular flat top sampling. I'm just giving a brief idea. So what will be the difference whenever we do the sampling? Okay, whenever we perform the sampling, then the sampled value will be uh, hold up to a duration of tau. Okay, up to a duration of tau, and then again it will go back to zero, and then again when it is sampled at this portion, again it will be hold, the same value will be hold up to a duration of tau. Okay, as compared to the pulse trend sampling, you will find that this pulse was taking the shape of the our massive signal. Okay, whatever be the amplitude of the massive signal, the same shape was taken by this pulse train also. But in this case, it is not there. Okay, in the case of flat top sampling, this top will be flat. Okay, this top will be flat. That's why its name is given as flat top sampling. So what we are doing is we are actually taking the sample at minus ts, and the same sampled value will be maintained up to a duration of tau. Okay, then again it will be go back to zero, then again the next sample will be taken at this point, and whatever be the magnitude at this point, it will be again maintained or hold up to a duration of tau. Okay, and therefore we will get a flat top. Okay, flat top. Okay, we are going to get a flat top. Obviously the magnitude of all each pulses will be different, but the top of this pulses will be a flat portion. Okay, as compared to the previous case in which the portion or this particular top of the pulses was not flat. Okay, so this way we are actually performing the sampling of any analog signal, and this way we are actually doing the time discretization of the signal. So I hope this discussion must be clear. In the coming section, I am going to discuss about how to perform the discretization of the amplitude. So please stay connected with the channel. If you find any difficulty, please drop your queries in the comment box. So stay connected with the channel, and thank you for watching this video.